Hey guys, I'm in the middle of implementing messaging layer security, and for that I've just finished my Hybrid Public Key Encryption implementation based on RFC 9180. So there are still some small tiny things left, but it's perfectly usable now, so I would like to show it to you. So it is it. It's about 1000 lines, 1100 lines long. It's basically the entire HPKE implementation. So you can see it's pretty nice. About like 1/3 of it is just TypeScript. So you can see that these are just TypeScript related stuff. But this amount of TypeScript magic really makes it nice to use and to work with. So I'm really proud of that. So let's try to use it. Obviously, we are going to have Alice and Bob talking to each other. Actually, it's not so much about talking each other because it's unidirectional. So Alice can only talk to Bob, and Bob can talk to Alice back, but it's going to work either way. So first we are going to need Alice and Bob. So I'm going to create two key pairs. So one for Alice. So for that, actually we need a Cypress suit. So let's create that. And we have all these Cypress suits that are recommended by the documentation and are implemented in my implementation. So let's try a simple 25519 curve with AS. That's going to be nice. And yeah, so now we can generate two key pairs for that Cypress suit. Alright, so now we have these key pairs. So now we need to create a context that Alice can use to send messages to Bob. So for that we need to create the Alice context, which is going to be created by context.setup base s. So as you can see, there are a lot of different modes. So the base s is just taking Bob's public key and creating HPK context out of like that based on that. There's also a PSK where you also have a pre-shared key. So there is a key that both Alice and Bob know, and then you use Bob's public key and the pre-shared key to create the context. There is the out key where you use Alice's private key and Bob's public key to create the context. So Bob knows that that context was created by Alice because it was also like Alice's private key was also used to create context. So it's like for authenticity. And there's also the out pre-shared key where you combine the authenticity and the pre-shared key. So that's like the most advanced type of context. But we are just going to use base. So let's create a base, and you either create one for the sender or the receiver. Here we create one for the sender. So for that we need the Cypress suit, we need a private, we need a public key of the receiver, which is Bob's public key, and we also need a random info. So this is like context specific info. It could be a message ID or a group ID or anything really. And for that I'm just going to create so info, which is just going to be random bytes, so 8 bytes of random data. And as you can see, I'm using the Noble crypto library. It's actually a very nice crypto library. So the entire HPK implementation is based on that. So now we have an info. So let's put that in. And now this will return like object with the encapsulated key that Bob can later use to create his own context. And we also have the context object, which as you can see is set to sender. So TypeScript already knows everything. So now we need the Bob context. She's basically the same, except we also need the encapsulated key. So that's going to be Alice context.enc. Alright, so we now have two contexts, and we can use this to create messages. So I'm going to create get a message. I'm going to like generate a random message, and for that we also need authenticated data because we are using ASGCM or GCM. So we could generate a random byte, but there is actually a set length for this AAD, which is based on the cipher suit. So this is where the TypeScript magic really comes in handy, because I can say ICS is equal to C to ICS. So this ICS object is basically just a better representation of the cipher suit, because here the normal cipher suit is just a number, but ICS is actually an object. So you can see we have all of these objects, and they are all based on the cipher suit, and TypeScript knows that. So if you change just the cipher suit, you change all of these values. So it's really nice. It's really easy to work with. So we have the ICS, and to get the AAD length, you just type in ICS.IAD, which is also a representation of the AAD like cipher, and it has the NN value, which is for the nonce. And if I hover over it, as you can see, it already knows that it's going to definitely be 16. Alright, so we have an AAD. Actually, let's create two messages and the second AAD, which is going to be AAD2. Okay, oops, right, forgot. So now we have the message and the AAD. So let's console log them just to see what they are. So Alice sends. So we send, actually no, not Alice sends. We need the raw messages. That's going to be MSG1, MSG2, AD1, AD2. I'm just going to say bytes to hex. Alright. I'm just going to console all of them. Console log all of them. So now we can say run the TypeScript pilot one. So let's do source MLS index.ts. And you can see all these messages. So this is message 1, like the raw message, not the encrypted message. This is message 2. These are the AAD values for it. Alright, now time to encrypt. So for that we need Alice context, and it's an object of the encapsulated key context, and we need to use the context here. And inside that we have the seal function. So this seal function is can only be used by senders, and we are a sender now, so that's fine. So we need the AAD and the message. So this is actually like a asynchronous function, so we need to await it. And now we can do the same for for the second message. And yeah, we need Alice context, not Bob context. Thank you. Okay, now we can console log these messages, encrypted messages. And if I do that, you can see that now these are one big encrypted messages. And you can see that they are changed because we use different AADs, and also the nonce for the AES changes. So the nonce is the initialization vector, and the AAD is just associated data. So now we can finally decrypt the messages. So for that we just run decrypted one is equal to Bob context, and Bob context is not an object, it's just context. We don't need the Bob context dot context. So here we have Bob context dot open. For that we need the AAD and the encrypted message. And this is also an asynchronous function, so we can decrypt both and then console log them. So now if we run this, so I actually made a mistake, my bad. So here when we set up Bob's context, we actually need Bob's private key. So we need to type bob.sk for secure key. So now it should work. As you can see, we successfully decrypted the message. So yeah, for this setup base receiver, we need the receiver's like private key, not Alice's public key. So yeah, that's kind of my bad for not reviewing the Copilot's suggestion. So yeah, but now it works. As you can see, we decrypted messages and got the original ones. Right, so that's very nice. But now let's see how we can use another mode of the context, which is going to be the out context. So we just need to replace the setup command with setup out s, setup out r, and setup out s is going to need a public key of Bob's, and at the end the secure key or the private key of Alice's. So of the private key of Alice. So we can type alice.secure key. And now Bob's context also needs the private key of the sender. I mean the public key of the sender. So that's going to be alice.pk. And it should it's all that you need to change. It should still work. Yeah, very nice. So now you can see it still decrypts, but now it's also using Alice's private key, so it's more authentic. So Bob definitely knows that this message came from Alice. The other mode is, of course, the pre-shared key. So with the pre-shared key, we can just generate a random key, pre-shared key, and it needs to be at least 32 bytes. So we're just going to generate a random key of 32 bytes. And now we can replace this with setup PS key S and setup PS key R. So now it needs a cybersuit, the public key of the receiver, which is Bob, info, like the pre-shared key, and the pre-shared key ID, which is also completely random, like it's from context based. So I'm going to also generate a random pre-shared key ID. So we can provide both here, the pre-shared key and the pre-shared key ID. And we also need this for Bob's contacts. Pre-shared key ID. Right? So let's try that. So I found a bug. So apparently setup PSKR was making a sender contacts and not a receiver. But now I fixed that, so you can see that TypeScript says it's going to be a receiver contacts. And it works. And at the end, we can, of course, combine the two together to get setup out PSK and setup out PSKR. So here we need the PSK ID and the PSK, and of course the secret key of the sender, which is Alice's secret key. Then we need Alice's public key. That's still going to work. I made the same mistake with setup PSKR, but now it will. So it didn't. So this function returned a sender contacts, not a receiver contacts. But now it works, and as you can see, it's still decrypting fine. But now it's using both a pre-shared key and Alice's secure key for authenticity. So yeah, that's basically it. And if you're wondering if this code is going to be published, I am going to publish it later, like one day. So you can enjoy this implementation in TypeScript. So anyway, have a nice day and goodbye.